All right, yeah. So if you could just introduce yourself and your research and how you got here, how long you've been at UMass, just kind of a brief biographical sketch.
Sure. I am Professor Erik Cheries. I've been at UMass for 5 years, and I run the Infant Cognition Lab. I don't know if I should look at you or
It doesn't either one. The other interviewees looked at me. It's not a problem.
Um, and yeah, I run the Infant Cognition Lab at UMass. I'm interested in the development of basic concepts, concepts related to number, concepts related to morality and social reasoning, physical reasoning, and I test babies as a tool for figuring out what these concepts might be like prior to language, prior to education, prior to lots of experiences in the world.
So what is there before language? It's a vague general question, but what are the big differences between their conceptualizations of the world prior to language and maybe an adult or someone who's not an infant?
Yeah. Well, language is an extremely powerful tool for thinking, and there's obvious benefits for memory. If you can encode something in terms of language, we know that that's a boost for thinking about events you've experienced. We also know like language is a powerful tool that gives you new ways of thinking about things that weren't really possible before language. So number is something that, in order to think the thought 1001 things, you need some sort of symbol system. So you need language. Even if it's not spoken language, written language, but you need a system of linguistic symbols, basically. So some of the work I've done, and lots of other people have done, is to see, well, what happens if you're a culture that had never invented words for numbers? Can you still think about numbers? And what is it like to think the thought 5? If you don't have the word for 5, can you still think of it? And the story, at least using that as an example, is that you need language to represent exact quantities, especially if they're as high as 1,000 or a million. But if you do experiments with babies, babies who are just newborns or babies that are 10 or 11 months, they still don't know words like 5 or 6 yet, they haven't been exposed to them. You can do experiments with them to see, are they capable of thinking of numbers in some different way? And these experiments show that you can. That babies, even before they have number words, have a gut sense that allows them to estimate things. So they can tell the difference between 8 dots and 16 dots. They know that 2 crackers is more than 1 cracker. You can give them a choice of which they would rather crawl towards, and you make it a memory game. So you place the crackers into buckets so they can't see them, but they have to keep track of them. And they know that 2 is more. They'll crawl to the one with 2. But you find some interesting limits. For example, babies can't seem to think of exactly more than 3 crackers at once. So it seems as though 1, 2, and 3 is fine. Once you go above 3, babies don't know exactly how many there are.
But they still have the relative weights. They know when one is more than the other.
Well, what's interesting, and I mean this gets into some of the nitty-gritty, if you show them 3 crackers over here and 2 over here, they'll crawl to the one with 3. But if you put 4 crackers over here and 2 over there, even though that should be easier, because there's even more, that's making it a bigger difference, they choose randomly. It's a counterintuitive result, but it's very consistent and it's been found in lots of different ways. What this research shows is that one way that infants and animals keep track of numbers is by thinking about the objects. Think of them as pictures, like picturing a graham cracker in your head, and then picturing another graham cracker in your head, and then picturing another. You can only hold so many things in your head at once. And that number for babies is about 3. For adults, it's only actually 4 or 5. You can think of if you've ever been on a soccer team or a basketball team or a sport where you only have 3 or 4 other teammates, and it's important for you to keep track of where they are because you want to be able to pass them the ball. It's kind of hard to split your attention to more than just 3 of those people. And you can show this in the laboratory using tightly controlled experiments. So that's one way that they're keeping track of number. They know that they have a picture of a graham cracker and a graham cracker, and they can compare that to a picture in their mind of just 1 graham cracker. They know that this is more. So that's one way that you don't need language. And you can also do numerical things that look like arithmetic. Like they know that if you have 2 crackers and you subtract another cracker, that there should just be 1 cracker left. So you can do experiments that show that. But another, call it a system that they have for keeping track of numbers, is much more general. Instead of keeping a picture in your mind of each item, you just have sort of a gut sense for about how many there are. So just like when you decide which line at the movie theater you're going to go to purchase a ticket, you don't look at every person in the line and try to hold them in your head at once and then compare it to this one. Instead, what you do is you look at that line and you say, oh, there's about 15. Or there's just about this much. Then you look at this line and you're like, oh, there's about twice as many over here. I'm going to go to this one. So babies, pigeons, rats, all these different animals that have been tested also have the same ability to estimate, just based upon the ratio. So babies know that 8 dots is are roughly half as much as 16 dots, but it's the ratio that matters. They're not able to think exactly 16, exactly 8. They know that 16 is more than 8, but they don't know that 12 is more than 8. So
Okay, that's okay.
yeah, so if the ratio between them is big enough, if it's like twice as much, then they know that there has to be more. But a 2 to 3 ratio is too small. So that's been studied a lot. And those are the 2 ways that babies can think about numbers. But neither of those ways allows you to think exactly 8 things. To do that, you need language.
Mm-hmm.
And so by the time a child is, say, 3 years of age, they're listening to Sesame Street and their parents, and they're learning 1, 2, 3, 4, 5, 6, 7, 8, 9. They're learning how to count. And it takes them about a year and a half to figure out what all those words mean. So they're going through this process of like inventing these concepts for numbers in their head. And then once they have those numbers, they're able to represent exact quantities. So language is necessary to think about exact large numbers.
Because of chunking, right? Kind of just putting it together in ways that, so if they didn't have the exact amount before, being able to represent that abstractly, a number abstractly in language, that's where the exponential growth comes in.
Yeah.
Right.
Yeah, language allows you to think abstractly about number in a way that's not really possible without it. And the cool thing is, you can go to, this isn't work that I've done, but other people who have done work looking at indigenous groups who live in relatively isolated parts of, say, South America, like along the Amazon River, where they're largely isolated from Western culture, and they never developed numerical language because they don't need it for their lives. They're hunter-gatherer groups. And so they don't have any word for 5 or 6 or 7. And you can go and you do experiments with them, and you see what they're capable of doing, and they look exactly like babies, and exactly like rats. So it's this powerful demonstration that language is a way for us to think new types of thoughts. And that's a cultural construction in that case. So that's just one example of number. And so what I do in my lab, or what we do as developmental psychologists who do infant research, is to look at different cognitive abilities and see what are those abilities like before and after language. What kind of experiences do they depend upon? And did we inherit them from our closest living relatives? So I've done work with rhesus macaque monkeys, other people do work with chimpanzees, and sometimes you see whether they behave like young human babies who don't have language as well. So that's kind of the strategy.
So in which areas was there sort of a similarity between the macaques and babies? What were some of the concepts that they handled similarly?
Well, there's a lot of similarity in terms of number processing without language. So, in a lot of ways, the babies think about number or are able to estimate numbers just like rats, just like pigeons, just like chimps or rhesus macaques. So there's a lot of overlap there. There's some dissimilarities, but in really broad strokes, it's more similar than it is different. For physical reasoning abilities, it's very similar. So you can do experiments with babies to ask whether or not they have basic intuitions about how objects should and shouldn't be able to behave. So do they understand that like objects are solid and they can't pass through one another, and an object can't blink in and out of existence. There's no teleportation in the real world. And so you can do experiments with babies who have had very little experience and show that they have some really simple intuitions about what's possible and impossible. And a lot of chimpanzees and other non-human primates share those same intuitions, even though they don't have language. So that's another type of thinking or another domain where there's a lot of similarity. Where they start to diverge is in sort of social understanding. So kids show phenomenon very early on of exhibiting empathy towards others and spontaneously like helping, sometimes working towards the same goal together.
What's the age that generally, there's obviously variation, but what's the general age that starts to occur?
For helping behavior?
Yeah, for the empathy type, yeah.
You can see helping behaviors, spontaneous helping behaviors around 14 months.
Wow.
So you can show the way these studies work is that a 14-month-old child is sitting in a room with their parents, and an experimenter comes in with a crate full of books. And without looking at the child, without asking for help, without making any eye contact, they walk across the room and they bump into a closed cabinet. And they bump into it and they look frustrated and they bump into it again. And what these experimenters find is that a significant number of these children who are just looking will march across the room, look at the experimenter, and open up the door. And then they do this spontaneously. That's something that you don't see chimpanzees do. You don't see macaques do this. They don't engage in spontaneous helping behavior like this. So we think that that's sort of a point of divergence. But there are some more basic abilities that non-human primates and humans share in common about social reasoning. But things like helping and sort of more advanced understanding of people's beliefs, that seems to be unique to humans.
What are some of the challenges that you face in your research and in working with infants as opposed to people that you can actually sort of communicate with, or obviously that's the point of your research. I mean, you want to see how concepts are evolving in people without language. But what are some of the challenges of that?
Yeah, well, obviously, yeah, because you can't ask them. You can't say, just think about number. Or for doing a question about moral reasoning in my lab, we can't say, who do you think is the nice character? Who do you think is the mean? You have to come
in
up
that
with
one, how do you intuit it? How do you figure that out?
So what people in the field have done is they've realized that even though babies can't tell you, they can show their maybe something like their moral judgment based upon their own preferences that they have. So one method that you can use is you show them some characters interacting, and one tends to help some character achieve its goal, and the other one seems to stop the character from achieving that goal. So there's two different characters, they look different, maybe they're different colors or different shapes. And then after the babies see this a lot, you can ask whether or not they judge one as better than the other by just giving them a choice. So you give them a choice between the two, you just place them in front of the baby, and you just see which one they reach towards, which one they would rather play with. So that's a really simple, direct measure. Sometimes we'll code their eye movements and their looking behavior. So which one do they look longer at, and as an index of their preference.
Do you ever use fMRI for it?
In my lab, we don't. And fMRI in general is difficult to use with babies because if you've ever been in a fMRI scanner, they're extremely loud,
Mm-hmm.
and you have to lay perfectly still. So that's not a useful tool at this point to
Mhm.
use with babies. But there are other physiological measurements that you can use, like ERP, which record electrical activity on the surface of the scalp. People also use a technology called NIRS, which involves shining an infrared light through the scalp of the baby and then measuring how much light reflects back. So there are these cool tools that you can use that can directly measure brain activity. And so people are more and more using those methods too. And we have some people here at UMASS that use those methods to ask related types of questions. But sometimes you don't really need to go out and spend, $500,000
Yeah.
because what you want to know is, what does the infant consciously experience? Do they have a preference for one thing or the other? And you can study that preference based on how they reach,
Mm-hmm.
how they crawl, how they look. But sometimes it is useful to know maybe which brain areas are active. Are they the same ones that are active in adults? So that's definitely an important tool, but it's not always necessary.
Absolutely.
And so it's not something that I use in my own work at this point.
So just two more questions. One, I just right before I met with you saw an article pop up about infants using Bayesian reasoning versus how adults understand statistics, and that children are actually, or infants, whatever it was, I think it actually was infants, are better statistical reasoners than adults and non-infants. Have you heard of that before? Do you have it?
Yeah, there's a lot of, there's been a wave of evidence showing that babies are statistically really savvy in lots of ways that are surprising. And they're adept at tracking statistical regularities in their environment. And they use that to make inferences about how things work. And there's a lot of examples of infants using statistical probabilities to figure out what things are words in the environment, patterns of speech, but also making inferences about sampling and probability. So you can show babies, in one of the easiest demonstrations, you show them basically a gumball machine that has some number of white gumballs and red gumballs, and say I showed you one and it was mostly white, like 75% white gumballs, but there are a few red ones. And now you sort of cover up the machine, and then you twist the coin slot to get out a gumball. And you do this once, and you get a red one. And you do it again, you get a red one. And you do it again, you get a red one. Maybe you get a white one. Babies will respond to that almost as early as 6 months of age, as if that's surprising, that they knew just by looking at it that it's improbable that you would get
That's amazing.
a sampling of 3 red gumballs to just 1 white one, when by looking at it, it seemed like there was a different ratio. And there's a lot of similar demonstrations using things that just aren't gumballs, and, but also using sounds, showing that one way that babies construct expectations about the world is by paying attention to probabilities.
Now, if that's true, if they are sort of better Bayesian reasoners than we are, why do we move away from that throughout development? So is that an adaptive quality to be worse in that regard? Why?
Well, I don't know. I'd have to look at exactly what evidence you heard that says that we're worse than the babies. We know that we have a lot of reasoning biases that often ignore what's statistically factual. There's a lot of examples of this. And a lot of these biases haven't been confirmed to exist in infants. So that's one way that adults might be biased away from statistical, factual reasoning, sort of doing what's optimal, where we might be compelled more by some sort of emotional biases. Some of those biases haven't been confirmed in babies, so that's one reason why we might think, you might have heard someone say that infants reason statistically more accurately than adults.
I'll send you the article too after we.
Yeah.
So,
But in terms, I mean, in general, a lot of the Bayesian analyses that have been found in babies have also been found in adults in different ways. So I personally wouldn't say in my reading of the literature that babies seem to be better at Bayesian reasoning. But they might not fall victim to some of the same biases that we have as adults. But a lot of this work has just been started in the last 5 to 10 years, and so we're still learning about what biases babies may and may not fall victim to.
So the last question I would ask is, what direction do you see your research headed in? What are some of the predictions that you think might be confirmed, or some of the studies that you might take on in the next few years?
Yeah. Well, in my lab right now, we have a lot of work looking at the ways that infants may or may not be biased when reasoning about other people, and especially in regards to how people look on the outside. So we're interested in sort of where stereotypes sort of start developing. So there's a lot of work in adults showing that when you first meet somebody, you look at their face and you make a lot of guesses about how smart they are, how competent they might be, how trustworthy they are, whether they're dominant or less dominant, a whole host of things. And they're not always accurate, but people mostly always agree on them. So they're very reliable. And so we're interested in where these things come from. When babies meet somebody, do they have an intuition about how competent or trustworthy they might be? So we're doing a series of experiments looking at, do babies prefer to crawl to a more trustworthy looking face or an untrustworthy one? If we show them someone who adults rate as very dominant looking versus someone who's less dominant, are they surprised when the dominant one steals the toys away from the other one, or the opposite? And so we're interested in whether or not babies judge a book by their cover. And then on the flip side, we know that adults have intuitions that it's what's deep down that really makes people who they are, especially when it comes to moral reasoning. And that you just can't change what you look like on the outside to change what you're like deep down. And so we're starting to do some experiments looking at whether babies have that sort of intuition that internal properties are more important. So this is related to sort of concepts of causal reasoning, like what do they think is the cause of people's behavior. And so we're doing some experiments where we show them some characters that behave in good or bad ways, and then we can do things like swap what they look like on the inside. So we can literally open up the characters and change some material and then see whether that changes babies' intuition. So we're really interested in sort of social reasoning biases and how they relate to phenomenon of moral judgment and sort of stereotypes, I guess.
Yeah, thank you so much. This is fascinating, especially where you're going with this, and I'll definitely be keeping up with it.
Awesome.